He's from the Department of Civil and Environmental Engineering at the Stanford University. And actually, about 5 years ago, I met Professor Borja because at that time I was invited by an official meeting in the Water Resource Agency at the Ministry of Economic Affairs. And at that time, I shared some of my project results on land subsidence. And actually, Professor Borja, he provided me a lot of valuable insight, particularly for the hydromechanical mechanism of land subsidence. So it's actually really a great pleasure to have Professor Borja here. So I think that I would like to invite Professor Gu, our Vice President, to make an opening remarks. So let's welcome to Vice President Professor Gu.
Okay, thank you, Professor Liu, today's host professor. And first of all, I'll be very honored and pleased to have our distinguished guest, Professor Ronaldo Borja from United States. We know Professor Borja for a couple of years. And before the formal introduction, I would like to say Professor Borja is one of the most decent person I ever met. That he gave us quite a lot of help, especially for land subsidence currently occurred in Taiwan area. He is also the most important consultant in the water resource agent currently in this land subsidence project. And we are very honored to have this opportunity to work with Professor Borja. Professor Borja is currently with the Civil and Environmental Engineering in the Stanford University. I think most of you guys know that the Stanford University is one of the best universities in the United States. It's also very difficult to apply. For me, I do not have the chance at my very young age to get the opportunity to go to the Stanford. It's so difficult. And so today we have such a wonderful chance to invite Professor Borja to come to National Taiwan Ocean University, especially in our department, Harbor River Engineering. And the student, you guys are very lucky to have this opportunity to have this very wonderful lecture that provided by Professor Borja. And today I would also like to thank you, our chairperson, Professor Shi, and the Dean of our International Affairs, Professor Fan, and our Associate Professor, Professor Huang, and our most good friend, and Dr. Behera, and all of our students, undergraduate student, graduate student, doctor student, to join this wonderful meeting. I would like to have your big hand first to welcome our distinguished guest, Professor Borja.
Thank you very much, and especially to Professor Liu and Professor Gu for their kind invitation. First time for me in Keelung. So, and you know one thing that I noticed here, because this is a campus setting, a university setting, the taxi driver dropped me off in the wrong place, right at the entrance of the campus, so I had to walk. And I didn't know where to go because this was my first time. So I asked people there, I just showed them my iPhone for the address, Louisa Coffee. And you know what? I was surprised because they all spoke English very well. So it was very easy for me to find the place. Well, in any case, I'm very glad to be here to share some of my research projects with you. And the title of my talk is Forecasting Land Subsidence Due to Groundwater Withdrawal in the San Joaquin Valley, California, and in Yunlin here in Taiwan. Now, Professor Liu told me that I can also talk about Stanford University. So that's what I'm planning to do. There are two parts to my presentation. The first part, I'm going to talk about my subsidence research. And then the second part, I will talk about my university, just to give you some statistics about the school where I teach. So to motivate my talk, I will begin with this image here of the subsidence in the San Joaquin Valley in California. This picture is very well known. You can see here a man standing right next to a post with markers, showing the positions of the ground surface in 1925, 1955, and 1975. During this period, the land has subsided by approximately 8 meters as the result of groundwater withdrawal. So you see here in the picture, Dr. Poland from USGS, who has written a lot of reports about subsidence in the San Joaquin Valley. And the photographer was Dr. Ireland, who was also a co-author of the same reports. Now, this slide here was taken from paper co-authored by Professor Liu, Professor Ku, and Professor Ni from National Central University, showing a plot of subsidence in the Yunlin area versus drawdown, recorded by multilayer compaction wells, or MLCW, at an elementary school in Tuku Township in the county of Yunlin. So the plot here shows that as the groundwater level goes down, the land experiences subsidence. What happens? Okay, I'm going to freeze here and not move a lot. It seems that the system is sensitive to my motion. So the plot shows here that as the groundwater level goes down, the land experiences subsidence. And as the water level goes up, maybe it's different. Now we see here that there is a recharge. The groundwater goes down and up depending upon the period of the year. What is noteworthy here is that the permanent subsidence continues to develop even when the drawdown was less than the previous years. Take the case of this curve here, for example, the blue curve right here. In 2021, the drawdown was so significant, and then there is a period of water recharge. And during that portion, there is a certain permanent subsidence that took place. So normally, we would expect that if the drawdown didn't go as deep, like in 2022, that there would be no permanent deformation. But as we can see here, the subsidence continues to accumulate. Right there. Now this slide shows plots of groundwater drawdown as well as the compression at the Panoche site in the San Joaquin Valley in California. So the drawdown plot is on top, and then the incremental compression is at the bottom. There is an obvious trend here of increasing drawdown, resulting in cumulative compression. The drawdown here is increasing, and then there is accumulation of compression. And then there is this period here of recharge, and we can see that the compression here has decreased considerably, but there is still compression taking place during that point in time. So normally, conventional models will predict that there will be no compression in the period where you have significant recharge. But we attribute this additional compression to secondary consolidation. Those of you who are taking soil mechanics probably heard about this term, secondary consolidation. Now, what I wanted to show in this slide is the subsidence forecast described according to the measurements. There are two types of instruments typically used for measuring the compression of a soil deposit. One is this extensometer right over here, borehole extensometer. It is a piece of rod that is established right deep into the bedrock. And you can actually measure the amount of subsidence by just locating the amount of, or the portion of the rod that has been exposed over a period of time. Now, it happens that in some cases, you don't encounter a bedrock. So in that case, the subsidence that we're talking about is just the change in thickness of the area covered by the instrument, which may not necessarily be the absolute subsidence, because the bottom of the instrument could also be subsiding. So from now on, I am going to use the term compression or compaction as opposed to subsidence. And that represents the change in thickness of the area, the deposit that is covered by the instrument. Now, on the right-hand side, you see here the abbreviation MLCW, multi-layer compaction well. And this allows us to measure the change in thickness of the individual layers, not just from the top to the bottom. So there are a couple of objectives in this presentation. First, we want to develop a mechanistic model or hydromechanical model for forecasting land subsidence. Forecast means we're going to predict the subsidence in the future and make full use of the field data from the San Joaquin Valley and from Yunlin to forecast future subsidence. So this is our mechanistic model. It is a one-dimensional column model, which is founded on the bedrock or on a fixed base. So whatever displacement we figure out from the top would be the change in the thickness of the deposit, and that will be our compression. Now, this model here is not meant to represent an actual physical pumping well, but it is just a one-dimensional model. We imagine that water is being extracted on top, and the extraction is distributed according to this function, which varies not only with Z, but also with time. Okay? Now, we can imagine this distribution here, the water extraction function, to be the result of the pumping from different wells surrounding this particular one-dimensional column model. The height here, H, is 300 meters for Yunlin, which is the depth of the MLCW, and 414 meters for the San Joaquin Valley, which is the depth of the extensometer. Now, we don't know exactly how that groundwater extraction function looks like. It is a function of Z, and it is also a function of time. So here we check and we assume that the function is distributed uniformly. Or triangularly, we will show later that it doesn't really matter whether you assume it to be uniformly distributed with depth or triangularly distributed. Everything will come out nice and easy once we calibrate with respect to the field data. Now, the triangle here has the largest value at 30 meters depth, and I'm going to show you the reason why that is the case a little bit later on. So we use here a coupled solid deformation fluid flow model, finite element modeling, in which each element is represented by 3 displacement nodes and 2 pore pressure nodes. So the pore pressure nodes are represented by the yellow circle, and the displacement nodes are represented by the red circles. So this is called a Q2P1 Taylor-Hood finite element. Q2 implies quadratic interpolation for displacement. P1 implies linear interpolation for pressure. Now, as far as the time dependence of this groundwater extraction function is concerned, we consider a Fourier series, a truncated Fourier series with coefficients that are going to be determined from back analysis. Next, we specify the boundary conditions for our one-dimensional column model. At the bottom right here, we assume that the displacement in the vertical direction is fixed. And on top, we assume that the vertical load is 0. So in other words, it is a free surface. So whatever displacement we calculate on top would be interpreted as the change in thickness of the column because the bottom end is fixed. Now, on top, we also assume that the pressure is equal to 0. It's called essential boundary condition, basically. And no load is called a natural boundary condition. Now, at the bottom, we're not really sure what the boundary condition there would be like. So we consider two possibilities. The first possibility is assume that P is equal to 0, which is called an essential boundary condition. Essential means that you are prescribing the value of the variable that you're trying to calculate. And then the other one is Q equals 0, which means that there is no flux at the bottom. So that is called natural boundary condition. And as I will show later on, again, it doesn't matter whether the boundary condition at the bottom is essential or natural. Everything will come out nice as long as we calibrate the model properly. So here are the governing equations for the one-dimensional column model. We assume an effective stress equation, which means that the total stress can be decomposed into an effective stress and the fluid pressure. Second, we assume two conservation laws. The first conservation law here is the balance of linear momentum. Everything should be in static equilibrium. And then the second governing equation here is the balance of mass, the law of conservation of mass. As we can see right here, on the right-hand side, it is not 0. So the mass of fluid is being injected into the system or extracted from it, depending upon you have withdrawal or recharge. So here we assume that the vertical strain is decomposed into 3 parts. An elastic part which can be recovered, a plastic part that stays, and then a creep part that persists as a function of time. And those of you who have taken geotechnical engineering from your professors here would probably be familiar with the void ratio versus logarithm of pressure curve. That is what we normally develop in the laboratory to figure out the compressibility of the soil. So here is our over-consolidated line, which is a line that you will obtain if the soil has been loaded to a higher load than what now exists. And then there is this NC line. NC stands for normally consolidated. This is what happens when the soil is experiencing the load intensity at the present time. So essentially the assumption is as follows: if the soil has been previously loaded to a pressure that is greater than the present pressure, it is called over-consolidated, and it traverses this straight line, flatter, smaller compressibility. And if the soil is young, then it traverses the normally consolidated line. So you have here 2 material parameters. One is the slope kappa, the other one is the slope lambda. And then the third line here represents the fact that the soil can also creep. By creep, what we mean is that the soil is continuing to experience deformation, even if the effective stress is constant. So these are the stress-strain relations that govern the boundary value problems. You could either have an elastic process or a plastic process, depending upon the position of the stress point on the E logarithm of pressure curve. And then there is also an evolution of what we call the pre-consolidation stress, which is simply a measure of how much maximum stress the soil has been subjected to in the past. And then there is also an evolution of the age of the soil. Now I'm going to ask you a question. If the soil has been loaded previously to a higher load and the load is removed, we say that the soil is over-consolidated. Now, if the soil is experiencing the amount of load at the present time for the first time, it is called normally consolidated. The question is, which of the two soils will behave in a more compressible manner? Is it the over-consolidated soil or the normally consolidated soil? Which one do you think will be more compressible? A soil that is old or the soil that is young? I'm willing to take any guesses. Who says old is more compressible? Who says young is more compressible? Who says I don't know?
Professor Borja, may I translate to Mandarin?
Okay, I am sorry.
Yeah, Borja just said the 基础工程上课，正常压密粘土比较容易压缩，还是过压密粘土比较容易压缩 ？NC 是正常压密粘土 ，OC 是过压密粘土。同学上过我们上礼拜的基础工程，我有讲过哦。来，要不要回答一下？来呀 ，please。NC 跟 OC 一样，正常是 NC，OC 是过压密，哪一个比较容易压缩？你 say no NC normal consolidated
Is more compressible.
Yes, yeah.
Correct. The normally consolidated soil is more compressible. And that's the reason why you have in engineering a process called preloading. The process of preloading is you apply a load first into the soil, you remove the load, and then you construct the building after you remove the load. Because once you remove the load, the soil becomes old. It becomes less compressible. And it becomes a better foundation for your structure. Okay? So these are the two equations that basically govern. One is for the old soil, the other one is for the young soil. And those of you who are going to be taking geotechnical engineering in the future will learn the difference between the two types of soils. Okay. Okay, so at the end of the day here, we have this one-dimensional column model, and we have a number of material and model parameters to calibrate. In this case, there are 10 model parameters to calibrate. 5 are material parameters, and 5 are the parameters of the Fourier coefficients, the truncated Fourier coefficients. So can you imagine a task where you have 10 parameters in the model, and you need to figure out the values of these 10 parameters? It's a difficult, very challenging task. And in order to come up with a solution, what we do is we employ machine learning. So in machine learning algorithm, you try to backfigure the model parameters from the field responses. And the field responses are the ones that have been recorded by the instruments that I just described earlier. So the steps in the machine learning algorithm are as follows. First of all, you do a forward analysis. In the forward analysis, you assume values of different model parameters. You can use Latin hypercube or some other techniques for generating random values of these model parameters. So that's called parameter sampling. And then you do a forward analysis, and then you collect all of these responses from your what is called mechanistic model. And then different other techniques here, synthetic trajectories, processing and normalization, train emulator. So this train emulator here is meant to be able to give you the values of these parameters for given values of input values, okay? So you're actually simulating the forward analysis, which is the mechanistic modeling, using this train emulator. Then you check for convergence. And then finally, you make the predictions. Okay, so this one here, we're going to talk about the subsidence in Yunlin, Taiwan. So we are going to test the proposed methodology to forecast the subsidence in a certain portion in Yunlin, in Tuku Township, which is currently experiencing severe land subsidence. So the most subsided area is in Tuku Township, right at the center of this figure, and is denoted by the star. Right there. We shall focus on the MLCW that is located at this point. The multi-layer compaction well. That's the instrument that measures the change in thickness. Now, fortunately, that instrument is also situated in another instrument that measures the pore water pressures. So this is a pictorial view, an aerial view of the MLCW location, which is denoted by the star, right over there. And then right next to a star is this green triangle where the pore pressure values are measured. So as you can see, they're one right next to each other. Now, according to the paper by Liu et al., there is this radius here, approximately 50 meters, where they said from statistical analysis that all these red dots here, which are your pumping wells, okay? So they state that the measured pore water pressure and subsidence at this point are influenced to a certain extent by these pumping wells that are going on within a circle of radius 50 meters. So that's a close-up view of the location of the instrument for subsidence measurement. And as you can see from this table right here, it shows you the depth of the well versus the number of wells in that area of Tuku Township. The pumping wells are primarily shallow wells. They're pumping water from a depth shallower than 30 meters. And that explains the point where we assume the triangle to have a maximum value of 30 meters. So these are just some statistics about the pumping wells within the Tuku area. These are the values of the material parameters that we assume to be constant all throughout the simulation in Tuku. Okay? Now, these parameters here were backfigured from the machine learning algorithm, and it is used to make predictions. Now, similarly here, these are the values of the Fourier coefficients Recall once again, the Fourier coefficients are used to define the time variation of this groundwater extraction function. And then at the end of the day, these are the calibration and prediction. The calibration here, the years are between 2017 to 2021. So that's a total of 1, 2, 3, 4 years of calibration. The dots here represent the actual measurements. Drawdown is at the bottom, compression is at the top. And we have here different possibilities, the triangular value or the triangle distribution of the forcing function, uniform, essential boundary conditions, and then natural boundary conditions. And as we can see right here, the red and the green lines and the black lines right here, those are the calibrated values. And what we're saying here in this figure is that it doesn't really matter what kind of distribution function you assume for F. As long as you calibrate the material parameters as well as the model parameters, then you will get, let's say, approximately the same response for drawdown as well as compression. So from 2017 to 2021, these are the calibration years. The prediction years are from 2021 to 2024 for a period of 1 to 3 years. And as we can see right here, once again, the dots are measurements, whereas the solid lines are predictions. The predictions are very close to the measurements. These are the mean values right here. And you have here some confidence interval as well. The confidence interval is meant to tell you how confident you are about the prediction. So the larger the confidence interval, for example, 90%, of course you will have to provide yourself more room for error. And that's the reason why the confidence interval here is increasing, getting broader or wider as the number goes up. Okay? Now you can also see here, the forecast is in the beginning of 2021. 2024 is 3 years down the road. So the farther you are in your forecast, the more uncertain the prediction will become. And that's the reason why the width of the confidence interval increases as you go farther away from the present time, which is 2021. The other thing that we can see here is that the confidence interval for subsidence or compression is narrower as compared to the confidence interval for the drawdown. To me, that is good. That is good news, because after all, we are more interested in predicting the compression rather than the drawdown. So the narrower this confidence interval, the more we can trust the results. This one right here, for example, shows that for the drawdown, it doesn't matter what kind of assumption you employ for the model. You're still very close to the dots. The dots are the measured values. Now you can see from this prediction here, again, this is the forecast beginning in 2021. All of these are predictions. The model did not anticipate the drawdown that took place, the more significant drawdown that took place because of a momentary period of drought between 2021 and 2022. So there was more drought, therefore people pumped more water during that time. As a result, the model underpredicted the subsidence or the change in compression because it didn't have that information that there would be that period of drought following 2021. So this underscores the importance of using the most recent data in order to make forecasts. Okay, so that takes care of the problem of Yunlin subsidence. Now let's go to the San Joaquin Valley in California. Now the San Joaquin Valley is much larger as compared to Yunlin. It covers approximately 26,000 square kilometers. In fact, in land area alone, the valley comprises approximately 3/4 of the area of the entire country of Taiwan. So you have here the valley, and what you see here is the subsidence that took place in the valley. Most notably, the redder the zone, the greater is the subsidence. And as a matter of fact, this portion right here in southwest Mendota is the site where we had taken the picture that I showed earlier. That's where the subsidence of approximately 8 meters took place. Now in particular, we're going to focus attention on this well right here. It's called the Panocha well, okay? And it is denoted by this symbol. You can see right here that the entire valley is subdivided into grids, rectangular grids, similar to the subdivision of lands. The first symbol here represents the position in the horizontal coordinate in this portion. And the second symbol pertains to the coordinate in the vertical direction. And then the third designation right there represents the specific position of the well within that rectangle. Now, we utilize the same machine learning algorithm to infer the material parameters, and here they are. Similarly, we use the machine learning algorithm to infer the values of the Fourier coefficients. Now, just to recall once again, what are the functions of these Fourier coefficients? These Fourier coefficients represent the time variation of the groundwater extraction function. Okay, so those need to be calibrated. And then we recall once again the situation that we were talking about. So right here, you have either drawdown as well as compression. What we're going to do is to investigate this portion right here, where you have continuous drawdown and then all of a sudden a recovery. And what I'm going to show is the accuracy of the model in forecasting subsidence and drawdown if there is a consistent trend. And at the same time, expose the weakness of the model in situations where there is a turnaround, a turning point from a period of drought to a period of recharge. So here are the calibration years as well as the forecasting years. 1, 2, 3, 4. 4 years again from 1962 to 1966. This is the consistent period where the drawdown increases. Period of drought. So these are the calibrated values for compression as well as for drawdown. And these are the prediction years, 1, 2, 3 years. 3-year ahead forecast from 1966 to 1969. And you can see from 1966 to 1968 that the compression as well as the drawdown have been predicted accurately because there is a consistent trend in the forecast. But there is a period of recharge following 1968. So now the computer model over-predicted the drawdown as well as the compression as a result of that turning point in 1968. Right there. So this is the turning point that I'm talking about. Okay? So we over-predicted the drawdown as well as the compression. And that was because we didn't know, the model had no way of knowing that there would be a turning point in 1968. And if you continue the prediction further, you will see that the forecast is becoming more and more divergent from the true measurement as a result of the lack of information on the part of the model about the turning point in 1968. Now, we conducted more analysis. I didn't include it in this presentation, and we showed that if we included the more recent data, that the forecast would be fine. Okay, so that concludes the first part of my presentation. Here are the main takeaways. The soil column model is insensitive to assumed pumping distribution and boundary conditions. And that is really a positive attribute of the one-dimensional column model. The confidence interval is narrower for compression than for the drawdown, which is good news, because after all, we are more interested in predicting compression compared to the drawdown. The longer-term forecast widen as time goes on, implying an increased uncertainty in the forecast. Calibration data need to be updated periodically for more accurate forecasts of compression and drawdown. So here I'd like to note that we have this paper here currently in review, and we hope that this paper will be published pretty soon. And the collaborators are Yang-Ching Sun, who is my doctoral student at Stanford, Professor Liu, postdoctoral Nancy Chow from NCKU, Qian-Xin Lai from Ministry of Economic Affairs, and Professor Lo from NCKU. Sponsors are the Yushan Fellow Program, MOE Higher Education Sprout, doctoral fellowship from the Department of Civil and Environmental Engineering at Stanford for my graduate student. So thank you for that part of the presentation. But it's not done yet. There is a second part. And the second part is a description, a short description of the school where I teach. This is Stanford University. It's called Hoover Tower right here. And this is a portion of the memorial of the Stanford Quadrangle, the main quadrangle. It is made of sandstone that has been quarried from a place at the university. The actual name of the university is Stanford Leland Junior University, in honor of Stanford Leland Jr., who is the son of Stanford Leland Sr. and Jane Stanford, the wife. He was a very prominent figure during those times. Politician, he became senator at the time, and he owns a railroad company, and that's where he got all of his wealth. So there's this interesting story about this couple, Leland Stanford and Jane Stanford. So they visited the president of Harvard University. And then they sat down and then discussed possible contributions, possible donation. So they asked the president of Harvard University, how much does it take for us to give you some significant donations? And then the president of Harvard just brushed them aside, thinking that they had no money. So they asked the president of Harvard, how much does it take to build a university? So now they're not donating. They are interested in knowing how much it takes to build a university. And then they were quoted a certain price by the president of Harvard. And then the woman told her husband, oh, I didn't know it's so cheap. Let us build our own university. And that's how it came about. I don't know if that story is true, but it's a worthwhile story to tell anyway. So it started in about 1890s. This is the Memorial Church, which is dedicated in honor of Jane Stanford, the wife. It's the centerpiece of the Stanford campus. And if you go inside, it's a marvelous piece of work. This is the interior of the Stanford Memorial Church. You can see right here that there is a dome. In 1989, there was a strong Loma Prieta earthquake that displaced that dome by a few inches. So they had to make some repairs of the dome. And it took them several years, almost 10 years, to repair the dome of the church. So it was closed for a while following the Loma Prieta earthquake. Here's another picture of the church. Now you might think that since Stanford is located in a seismically active region, that the structures may be prone to collapse in the event of an earthquake. They actually did some meticulous reinforcing of all the parts in the campus. So what they did was they removed this shell right here, the sandstone shell, and then they reinforced it with rebars. So it's reinforced. It's quite an expensive task because you have to do everything meticulously, and then they put it back. So most of the buildings at Stanford are earthquake sort of like resistant as a result of this project that they conducted following the Loma Prieta earthquake. So here are some statistics. Established in 1885, opened in 1891. The official name is Leland Stanford Junior University. The university has a total, as of fall of 2025, a total of 7,289 undergraduate students, 10,025 graduate students. So there are more graduate students than undergraduate students, and the proportion is actually increasing. In other words, the undergraduate population is getting a little bit smaller, and the graduate population getting a little bit bigger, for a total of 17,314 matriculated students. There are 2,402 faculty members as of fall of 2025. 1,781 are academic council members. So these academic council members have the right to vote in case there is an issue related to the university. 20 Nobel laureates and a 7-to-1 student-to-faculty ratio. So what you want for that ratio is for the number to be small. The smaller that number, the more time the professor has for each student. If that number is large, then there will be too many students per professor, and that may not be good for the professor nor for the student. So the student-to-faculty ratio is 7-to-1. There is a total of 8,180 contiguous acres of land, so it's a vast amount of land. Over 600 buildings within the Stanford campus, and about 97% of the undergraduate students live on campus. As a matter of fact, freshman students, first-year undergraduate students, are required to stay within the campus as part of their educational experience. There is a total of 7,500 plus externally sponsored projects, 10.3 billion total operating budget. These are the budgets used for the faculty salary, for the expenses of the department, and so on. And $40.8 billion of endowment. So the endowments produce some payouts, and the payout is approximately 5%. So you're talking about $2 billion of payout, which is approximately 1/4 of the total expenses. the total operating budgets by the university. So what is the structure of the university? There are 7 schools. Now the departments are under the umbrella of each school. I don't know here at NTOU if the structure is similar. There are programs within the department. So it's the university first, and then the school, and then the department. And then within the department are the programs. So here are the 7 schools. School of Business, Sustainability, Education, Engineering, Humanities and Sciences, Law, and Medicine. Those are the 7 schools. And you will see right here that CEE, which is the Civil and Environmental Engineering, where I am affiliated, belongs to 2 schools. So the CEE department is only one of 2 departments under the umbrella of 2 schools. That means to say we are 50% under sustainability and 50% under engineering. The other department that is under the umbrella of 2 schools is bioengineering, under the umbrella of medicine and the umbrella of engineering. Now, not all of these schools offer an undergraduate program. The only schools that offer undergraduate programs are the Sustainability School, Engineering, and Humanities and Sciences. The other schools only offer graduate degree programs, master's as well as PhD. Undergraduate enrollment are as follows. The total matriculated student is 7,289. 51% are women, 49% are men. So there are more girls than boys for the undergraduate population. You can see here 53% of the undergraduate students are undeclared. They have no major because the first 2 years as an undergraduate student are years where the students will decide their major. They only are required to declare their major at the beginning of their junior year. And that's the reason why 50% of the students are undeclared, undergraduate students. Now, those who have already declared their major, Humanities and Sciences, 25%, Engineering, 21%, and Sustainability, 1%. So the School of Sustainability has a small undergraduate population, but they have big graduate population. So these are the most popular majors in the Humanities and Sciences: Human Biology, Symbolic Systems, Economics, Biology, and Political Science. Now, for the graduate population, total matriculated students is 10,025. 47% are women, 53% are men. So now there are more boys than girls. 36% are international students. 64% are US students. Total graduated in 2025 is 3,688 students. And of the students who graduated in 2025, 73% obtained their master's degree. 27% obtained their PhD degree. So there are more master's students than PhD students. Now, in the School of Engineering, where my department belongs, here are the departments: Aeronautics and Astronautics, Bioengineering, Chemical Engineering, my department, Computer Science, Electrical Engineering, Management Science and Engineering, Material Science and Engineering, and Mechanical Engineering. And guess which one is the most popular major? Computer Science, because we're in Silicon Valley. Stanford is in Silicon Valley. In the School of Sustainability, here are the departments: Civil and Environmental, Earth Systems, Energy Science, Geological Sciences, Geophysics, Oceans, and Social Sciences. So yes, we have a Department of Oceans, just like in this university. It's under the School of Sustainability. So in my department, these are the programs: Atmosphere and Energy, Environmental Engineering and Science. And this program right here also covers hydrology and fluid mechanics, structural engineering and mechanics, and sustainable design and construction. So in our department, we always joke that the department is composed of two sides: the wet side and the dry side. The dry side includes structural engineering, construction. The wet side includes fluid mechanics, environmental engineering. That's how we divide ourselves. But my field is neither wet nor dry, or both, maybe, because geotechnical engineering has both solid and fluid. Faculty, there's a total of 2,402 faculty, 1,781 are academic council members. The rest are not academic council members. These are the adjunct professors, the consulting professors. They don't have the right to vote. 34% are women, 66% are men. So you can see here that the disparity is more significant in terms of gender for the faculty. 59% are white, 19% are Asian, 6% Hispanic Latino, 3% Black Asian American. And you know, only in the US where you can see all of these statistics. Typically in countries like Taiwan, Philippines, you know, we're all the same. But in the US, it's the land of immigrants. So you have all of these divisions. So my areas of research include geomechanics, geotechnical engineering, computational mechanics, and geohazards. And these are just some statistics to tell you about undergraduate admission, which does not pertain to this group of people. Okay, so these are the admissions criteria. They are done by the university. Meaning to say the university admits the undergraduate applicants. So the admission committee is very much anonymous. You don't know who they are. Of course, they are members of the faculty, but their identity is secret in order to protect them from pressure, not only from the students applying, but also from the parents. So you don't know who these people are admitting the undergraduate students, applicants, okay? So graduate admission, on the other hand, is done by the department. So here, it is possible for you to contact the faculty directly. And you will know who will be admitting you in case you're interested in applying to the graduate degree program. So these are the freshman application requirements. Again, it doesn't pertain to you. For the graduate degree program, we offer MS and PhD just like in this university. Here are some pictures of the campus. This is called the New Science and Engineering Quad. It's made up of 4 buildings representing a quadrangle. So this is our building right here. It's called Y2E2 building, 2 Ys and 2 Es. Yamasaki Environment and Energy Building, donated by Jerry Yang from Yahoo, and his wife, Akiko Yamasaki. This is a portion of the science quad. This is where the dean's office is located, and this is our building right here. So you see that the buildings are made of arches, very much like Spanish architecture. Modern version of the arches that I showed you earlier. So this is a picture overlooking the old, or the main quadrangle right there. The science and engineering quad is in the foreground. As I've said, undergraduate students, 97% live on campus, and these are some of the dormitories where they live. And each dorm here or each house has a certain theme. For example, this particular dormitory here is for Jewish students or students who want to study or learn about Jewish culture. Again, this one here is undergraduate student housing. And all graduate students are housed also on campus. This is called the Escondido Village Graduate Residence, the tall buildings, also within the campus. Okay, so that ends my presentation. Thank you very much.
So thanks for Professor Borja's very insightful presentation. So does any audience have any comment or some question?
Yes,
Yes, okay. Now.
Professor Borja. Wait. Professor Borja, thank you for your presentation. You mentioned the use of the confidence intervals to quantify prediction uncertainty. However, I'm curious about the robustness of the model under conditions that may fall outside the calibration data set, such as extreme drought events, abrupt groundwater policy changes, etc. So how confident are you that the model can maintain reliable prediction? Thank you so much.
Thank you. Hello. Yeah. Hello. Can you hear me? Okay. Yeah, thank you for the question. I think it is a very important question. As I pointed out earlier, it is extremely important to include the most recent data for calibration because the model really does not have a way of knowing whether there is going to be a certain turning point. That's really the problem with prediction. We need to have some other indicators to tell us whether there is going to be a heavy period of rain in the near year or so. So one thing that we can use or we can do is to tie up our predictive model with the weather forecast in order to figure out whether there's going to be an upcoming period of rain or an impending period of drought. But that is always the challenge with making a forecast because the prediction is very much tied up to the environmental condition. I also emphasize the importance of including the most recent data in our forecast. In the revision of the paper that I showed you earlier, we made forecasts for the San Joaquin Valley that are more accurate compared to the forecast, not knowing exactly whether there is going to be a period of recharge. And in that forecast, our calibration years include 1967 to 1966 to 68, which is the two period of drought, followed by 1968 to 1970, which is two periods of recharge. So in that case, the prediction of the model has improved because now the model knows that the drought ended in 1968, okay? But there's also this issue of how much weight are we going to place on the most recent data. Because so far what we have done is to assume that the weights of all of these calibration years are the same. But if we place emphasis on the most recent data, then we found out in our prediction that the forecast turns out to be more accurate because that really depends on the current situation in the field. So to answer your question, the best way we can do is to include the most recent data and go from there.
Do you consider about the earthquake? Because Taiwan has a lot of earthquake happen very frequently, so sometimes maybe change the groundwater, the depths, right?
I don't know if I heard you right, but did you say earthquake?
Yes.
Okay, so earthquake could also give rise to different possibilities. For example, if the ground surface is not flat, even if it is gently sloping, there is always a possibility of lateral displacement, which could bring about additional subsidence. And one thing here that I didn't point out was that because we had a one-dimensional model, that we ignored lateral fluid flow, which could also influence the subsidence. But at least from our standpoint, this is a significant step, because from our literature survey, we haven't really come across any robust mechanistic model out there as far as prediction of subsidence is concerned. There are a lot of models dealing with landslides, but not very much in the area of subsidence.
Okay, thank you.
Thank you.
Thank you for your answer.
So anyone have further comments or any question? Wei Tang. He's undergraduate student.
The model is very complicated. How
to assign the parameter? Do you mean the soil property? Soil property is so heterogeneous. How to assign the soil property?
Yes.
Okay, so if the question is, or if the comment has to do with the fact that the model is too complicated, my advice is for you to do graduate degree program. You apply for a graduate degree. In other words, apply for admission. Pursue a master's degree. I know you're an undergraduate student, okay? So you pursue a postgraduate degree. So you will learn much more. When I first came to Stanford as a graduate student, everything to me was so complicated. But you learn as you mature, as you get exposed to this different kind of education. Okay, so if you're really interested in learning the model, I think that is a challenge for all of you to consider pursuing a graduate degree program.
Okay, thank you. So anyone have further comment? Mihara, 邱老师，顾老师，
Okay, I just want to express my appreciation to Professor Borja, who gave us such a nice presentation, and also welcome Professor Chu, he just joining us the meeting. And I just a little bit surprised by Professor Borja when you introduced the Stanford University, especially you talking about the fundings. It's made me open my big eye. I just admire that the Stanford University has such a nice funding, especially I saw that the funding is about 10 billion, right? 10 billion US dollars, not Taiwanese dollars, 10 billion. And the endorsement is 40 billion. Is that right?
Yeah, that's the one that's generating interest in the bank.
Oh.
So the interest in the bank is the one that we use as we consider a payout.
Payout.
To support the faculty, to support the administration.
Okay. It's an annual payment or is that
Annual payment is about $2 billion.
2 billion? Okay, 2 billion. 2 billion is also amazing. It's US dollars. Compare if you transfer to Taiwanese dollars, it's about 600. Too big. It's confused me. But I think it's really nice. The university has such a nice funding because with fundings you can do a lot of research. And I'd like to thank you, Professor Borja, to give a very nice introduction of the Stanford University. Even though I just mentioned that when I was young, I do not have the competition to go to the Stanford. But I believe the undergraduate student in our department or in our university, I will still encourage you pursue your graduate study. Especially if you have a chance, you can go to the United States. I think Stanford is one of the best universities that you can be put in your list of your wishes. Okay, and finally, is there any question that our students have any other questions? Not just land subsidence, but also any other questions related to the graduate studies, something like that. If you are planning to go to United States or Stanford University for the application. Any questions? No? No? Okay. And because we have a certificate for today's presentation, I think I would like to invite our chairperson. He's my boss in our department. He's supposed to be the one to give the certificate.
President.
Yeah.
You should be.
It's okay. You are the boss.
Okay. Together. Oh, together. All together. Yeah, all together. Professor Chu.
你开始，等一下。
Okay. One, two, three. Okay. Thank you so much.
我们拍一张大合照，请后面最后一排的同学帮忙站起来，倒数2排的同学帮忙站起来，谢谢。
所以你们要布条吗？来，你们蹲下。邱老师这边还有一个位置，帮我。
Professor Chu, come.
主任、副主任。
好，我们等一下。拉，对，上面拉开。好 ，OK， 后面的同学你们可以站起来哈。好 ，OK， 来，这边来，1、2、3。
好，俊然你喊一下 3, 2, 1。3, 2, 1。Okay. Thank you. Let's give a big hand to you. Thank you so much.
There's a local souvenir. Belongs to the most famous.
Oh yes, I like that.
Prepared by
Professor Wu, this is our gift from
the department.
Shrimp. It's dry shrimp. You can eat directly in the snack.
Okay, great, thank you.
I see yours.
For you. Yeah, okay.
Okay, yours.
那个俊安，我们拍一张照片，你跟那个帮忙。
With this one?
哎，主任，你们拍。
Just this one?
You don't have anything.
谢谢啦。原来吃中餐做很辣。
Maybe while eating.
One, two, three. 快想。 我等下看就
那个也一直没有。
You want to take this? You want to take No need, no need. 对啊，我是在隔壁厅啊，对面的那个。对，把它封面都那个，对哦，没有影响大家。刚好光线打到。对啊，上一次我拍过去还不错。我看。Also, you see our team.
Already?
Yeah.
5 years ago. Okay.
He was there?
Yeah, he was in our project. Yeah, I used to be in the team, but because you have bigger projects. No, afterwards, so.
He doesn't need our project.
No.
I think you should go back to United States frequently, right? Every year.
You mean where? Yeah, I'm very good from COA. Yes, I went.
In what department?
Do you know?
But do you know Professor Chen used to be?
Yeah.
Was he there when you were there?
Yeah, I was working with my
Yeah. I don't know personally.
第四例。需要喝盖的同学哈，记得点名。然后刚刚有发了一张问卷，请你们记得要填哈。那等一下的话，那张问卷帮我交到前面那边好吗？那你们就今天的课程就会结束这样哈。交到前面那边。
So my students